Hi everyone. Addressing your feedback from today's discussion about reaction kinetics and reaction mechanisms. So I got a bunch of questions here. How do you determine what the system is when you're trying to decide whether or not a reaction is endothermic or exothermic? So this is in regards to the last question we had when we were trying to decide. I was demonstrating with the chocolate whether the chocolate is going to a higher energy state or a lower energy state, or whether somebody's energy is going up or going down. So basically the question is, how do you decide what the system is and what the surroundings are? And that is admittedly open to interpretation. You can define your system however you like. There are frequently one way is more logical than another. And generally, I personally would prefer to define my system as a closed system. A closed system is a system that can transfer energy, but not matter, not material. So literally, if you had like a sealed, I'm looking at my desk right now, if I had a sealed can of soda, I can't get any material in or out of the soda, but I can heat the soda up, I can cool it down, or rather I can heat the can up, I can heat the can down, cool the can down. So I can change its temperature, I can have heat go in and out of it, but no material, no mass is changing. So I usually try to define the system such that the mass of the system is constant. So I would, in the particular context we had today, I would prefer to say that the chocolate was our system, because the chocolate's mass doesn't change as it goes from its wrapped state to its unwrapped state to its eaten state. Its mass, until it undergoes chemical change, its mass is constant. Similarly, when we were talking about which one is more disordered, a large tree or a baby sapling, I argued that the tree had less disorder, because all of the carbon dioxide that, or rather I should say all the carbon that made up the body and the trunk of the tree, when it was a sapling, all that carbon was in the form of gaseous carbon dioxide. So people were asking, well, why would you include the carbon dioxide as part of the system? And again, it's because, well, we like to think of the system as having a constant mass. If we think of the large tree as our system, we want to maintain the boundaries of that system. So even though the matter wasn't originally in a gaseous state, we'll still consider it part of the system such that we maintain constant mass for our system. So yeah, generally, how would I choose it? I try to identify and set up the bounds of the system such that only energy is transferred in and out of the system, not matter. Does the time length of an intermediate step change anything? So a short answer to that is no. No, it doesn't. Caveat there is you normally don't talk about an intermediate step. You can talk about elementary reactions, elementary steps in a reaction mechanism, and during the course of one of those elementary steps, you may produce an intermediate species. I would say that molecules, compounds can be described as intermediates. Reactions are not described as intermediates. So you don't really talk about the time length or the rate of an intermediate. You can talk about the average lifespan of an intermediate, but generally no, that is not really directly related to the rate of the reaction. There can be, but generally there isn't any correlation. So I would say no to the question, is there any does the time length of or the length of the half-life or the lifespan of an intermediate is not really dependent upon anything else in terms of the reaction rate. What was the correct answer for the first question you did? So the first question I gave was about this reaction, two hydrogen sulfide molecules reacting with oxygen to produce two sulfur molecules and water. And the question for this was, what is the reaction rate law? And the correct answer, it was a multiple choice question, the correct answer was D, none of the above, because given just the chemical equation, you cannot predict the rate law. So there was no way to actually answer the question in the sense that there was no way to determine the correct rate law because you don't have enough information to determine the correct rate law. So the answer necessarily was D, none of the above. Again, that's because you cannot predict a rate law just by looking at the balanced chemical equation. You have to go and do experimental measurements and determine how the rate depends on the concentrations of each species. Now, I admit I actually did spend about 20 minutes trying to search Google to figure out what the rate law for this reaction is, and I admit I couldn't find it. So I will plead ignorance that I don't actually know what the correct rate law for this reaction is. So I apologize sincerely for that. How do you know the speed of each of the steps in a chemical reaction mechanism? So like we talked about today, how in a reaction mechanism, normally one of the steps, one of the elementary reactions is significantly slower than the other ones, and that's what sets the rate for the entire experiment. And your question is which of them, how do you predict which of them is going to be the fast one? So there are some ways to predict it. There are some ways to predict it, but generally speaking, the rate of the reaction, any reaction, is determined by concentrations It depends upon the concentration of your reacting species, and it also depends on the rate constant itself, which sets the fundamental rate for the reaction. The rate constant is determined from the Arrhenius equation, which says that the reaction rate constant is dependent upon the temperature, the activation energy for the reaction. So if you have a reaction profile, and you have the energy, the idea is as you go from products to reactants, your energy is always going to go up before it comes back down. Now, whether it ends up being a net endothermic process or a net exothermic process doesn't matter in terms of predicting the activation energy. The activation energy is always the difference between the top part here, which we call the transition state, and either the reactants, you talk about the activation energy for the forward reaction versus the activation energy for the backwards reaction. So anyway, yeah, I would call this gap here the activation energy for the forward reaction. So the magnitude of that activation energy is going to determine the rate constant. The last term here is the collision factor. So the idea of collision theory is that reactions occur when molecules, reacting species, collide with each other. If we work from that assertion, then the rate of the reaction is going to depend upon how many of those collisions, what fraction of those collisions have the necessary energy to go over the activation energy barrier. So this whole term here essentially represents the fraction of collisions that have the correct energy. The A term here represents the total number of collisions. So we call this again the collision factor. Also sometimes just called the pre-exponential factor because it comes before the exponential term. But the collision factor itself is based on two other factors, which are the collision factor and the orientation factor. So this is actually the collision frequency, not the collision factor, I should say. So this in its most gross state, determines how many collisions are there per second between the reacting species in a chemical system. So that overall is going to tell you just how many collisions are there per second. Not all of those collisions will successfully result in a reaction. Partly because they might not have enough energy to go over the activation barrier. So this whole term takes into account the fact that not all of the collisions will be successful energetically speaking. This last term here is the steric or orientation factor. And that basically is a factor that takes into account the fact that reacting species need to actually collide in the correct orientation for the reaction to be successful. So case in point, if we think of this as one reactant and another reactant, and we think of this, them coming together as the product, so I could represent that reaction like this. They start as two separate species and they come together to make a new chemical species. That collision is only successful if they hit in the right orientation. If they are coming together like this, but say the marker cap is reversed, they're not going to successfully collide and stick together. They have to actually hit with the correct orientation. So your question was, how do you know the speed of a particular elementary reaction? You can theoretically predict it if you can predict the activation energy for that reaction, for that elementary reaction, and you happen to know the collision frequency, and you happen to know the orientation factor, then in theory you could predict it, the relative speed of the reactions. Now in practice, as in a general chemistry course, we won't be asking you to do that type of an analysis. That's pretty intensive, and I don't think it's really getting to any deeper understanding. But one thing I could ask is something like this. Given a reaction profile, well, I'm not going to ask this question on the midterm because I said I wasn't going to put mechanisms on the midterm. I'm not going to put mechanisms on the final, but you could ask a question like this. Let's say I looked at a reaction profile for a two-step reaction mechanism. So this is a two-step reaction mechanism because I have two transition states. This point here would be my reactants. These would be my reactants. These would be my products. So it's a exothermic reaction because the products end up lower in energy than the reactants. And this little saddle point, or not, I mean, it's not a saddle point, but this local minimum here is going to correspond to our intermediate. So these are, again, chemicals or molecules that are produced and are stable. They exist in the reacting system, but they don't persist. They're eventually consumed and turned back into products. So this reaction has two steps. The first step is going from reactants to the intermediates, and so this reaction has that as its activation barrier, so I would call that EA1, and this, it represents the activation barrier for the second step in the reaction mechanism. And so, given that information, you could make a logical guess as to which one was the rate determining step, because the rate of the reaction is inversely related to the activation energy. The higher the activation energy, the lower the rate, the fewer number of particles that are going to have that high energy cost to actually initiate the reaction. So this first step here, I would predict to be the slow or rate determining step, simply because it has a significantly larger activation barrier than the second step. But beyond that, there really is no easy way to predict which is going to be the slow step. How do you know if a reaction is an elementary reaction or a net reaction? So the most obvious way is if I present it as a reaction mechanism. If you see it as part of a reaction mechanism, it's definitely an elementary reaction. So that's sort of like a most blatantly obvious way that you can determine it's a reaction mechanism. Or that it's an elementary reaction, I should say. The other way to think about this question is, how can you tell, let's say I give you a net reaction, and I ask you, is the reaction mechanism for this the same as the balanced reaction? Let's say, let me give you let's say this is my chemical reaction. How can I predict if this actual net reaction is the same as the elementary reaction? Meaning that the elementary reaction is the exact same as the net reaction. The only way you can predict that, the only way that you can prove or assert that the reaction happens is if you know it happens in one step, So you would need to do a couple of things. It would only be true that this is the only elementary reaction if it occurs in one step, and you would need to check that the experimental rate law matches the rate law for that one elementary step. So if you actually measured the rate law and your experimental rate law was A times B, then that's possibly an indication that the rate law a possible indication that the reaction mechanism, the single elementary step for this net reaction being the same as the elementary reaction, this is one vote in favor of that, because if this is your experimental rate law, it's also the same as the rate law you would predict for the elementary reaction. And then you need to also see, are there any other chemical species being produced? Are there any intermediates, any possible later reactions that might occur that we didn't predict? That's something else to consider. But beyond that, there really isn't any trivial way to determine whether the net reaction and the elementary reaction are the same thing. You need to basically be given some indication, and that indication will be that it's part of a reaction mechanism, that it's an elementary reaction. How does temperature affect the slowest rate? Short answer is that it isn't going to change it from not being the slowest rate. It will always be the slowest rate. So raising the temperature tends to speed up every single reaction. No matter what happens, you raise the temperature and the reaction rate increases. So if I have a multi-step reaction, and this is the slow step, its reaction rate is going to increase, but so will the reaction rates of every other chemical reaction and every other elementary reaction in the reaction mechanism. And those other reactions, if they started faster, they're just going to become even more faster. Ugh, bad English. They're going to become even faster. They're not going to suddenly become slower than the slowest step. So they all increase with temperature, but the slowest step remains the slowest step. Point being that just because you raise the temperature doesn't mean that you fundamentally change the reaction mechanism. You won't fundamentally change the rate law for a reaction. So the answer is it doesn't really have any effect. I mean, it has an effect on the slowest step in the sense that it causes the slowest step to become faster, but it doesn't stop it from becoming the slowest step. It will remain the slow step. Okay, so that's all the questions for today's lecture. If you have any other ones, please let me know. I'll be available in office hours throughout the whole week. Otherwise, I will see people on Wednesday. Have a good day.